Hi, I'm John McMillan, and welcome to today's webinar demonstrating modern PCB design accelerators in PADS Professional that get your products to market faster. You know, from cell phones and wearables and in every industry for today's competitive electronic products, bringing products to market fast and first is critical for success. What you may not know is, if you're not using advanced techniques for things like high-speed routing and tuning, placement planning groups, design reuse, plane generation automation, and more, that it can delay your design completion time up to 70% or more. And if you're not using these advanced techniques, you're essentially giving your competition a competitive advantage. That's what today's webinar is all about. So, to see how advanced PCB design capabilities empower small teams, independent designers, and engineers to fast forward product creation with powerful PCB design features that give you a competitive advantage and reduce your product design cycles, avoid costly design respins, and get products to market faster, I'll turn this webinar over to one of our technical marketing engineers, Brent Klingforth, to demonstrate how. Brent?
Thank you, John. I would agree that if you're not taking full advantage of the automation capabilities available in today's electrical engineering tools, you're delaying product development. I've been a PCB designer for 25 plus years and cannot imagine going back to designing a PCB like I was in the late 90s or even early 2000s. EDA stands for Electronic Design Automation. But it seems like many designers today are not continuing to advance their knowledge of automation technology, which, as you mentioned, can reduce design time by 70%. In some cases, 90% when implementing auto routing technology, which we'll see an example of later on in our presentation. Most designers start a PCB by grouping parts using cross-probing from the schematic. However, using a spreadsheet-based view like Component Explorer allows us to quickly see information about our components and groups created for each circuit. These groups can be created either in the schematic or PCB. We'll be starting this design using MCAD collaboration. As with most designs today, the I/O interconnect interfaces with a mechanical enclosure. As you can see, this dramatically reduces placement of mechanical critical components. Additionally, changes can be passed between each domain. Creating a rough placement with interconnect using groups allows us to plan ahead. As you can see, when placing groups, net lines vary in thickness based on the connection count. The circle size is defined by the component count and size of that group. More importantly, we can see net topology, which helps determine routing paths and where there may be congestion before we place a single part. Using hierarchical groups allows us to break up the large circuits when some of the parts will be placed on the bottom. Most every schematic and PCB tool can cross-probe, assisting with placement. However, to simplify this task, we can use an embedded schematic viewer with simplified controls. Passive components always pose a challenge to place with their large number in the design. Binding via the schematic using sequential placement makes it a snap. While placing a termination resistor for this connector, we'll use alignment technology to speed placement. Notice while placing each part that lies on the same axis as another, the part snaps to the edges of a placed component. At some point, we always need to move a group of parts. Because we created groups for the majority of the parts in this design, we can use visible group outlines to move a selection of components easily. Groups can also be assigned to top or bottom placement, as well as rotation, again simplifying placement. Unlike component distribution in most tools, layout can auto-arrange parts for a group using their placement outline and design rule. A second method for placing parts is to right-click over the refdes of a placement group and choose from the list. This minimizes mouse movement and facilitates faster design. If possible, we as designers should try to reuse circuits from one design to another. This is the ultimate in time-saving technique. Design reuse can be done from both schematic and PCB. For this design, we have two USB interfaces that use the same circuit. For layout reuse, all the items selected can be saved from a design which includes part placement, traces, planes, vias, drawings, keepouts, stack-up, manufacturing data, etc. If refdes values are the same, you have the option to automatically choose the correct parts. If there's no refdes match, you can try to auto-resolve the part selection. Lastly, you can choose the appropriate part from a list if more than one exists. Once placed, the circuit can be customized based on the surrounding circuits. Let's move on to constraints. Many designers try to avoid this process except for the basics, as they find it time-consuming and difficult. Constraint Editor can be started from either the schematic or layout with equal capability. To start, we'll make a net class the basis for all clearance rules. We're missing our 100 ohm differential pair class. Once created, we'll assign the Phi and HDMI differential pair nets using two different selection methods. First from the assigned function in CES, the second by cross-probing with the schematic. Next, we need to define and set the trace width and trace-to-trace gap for differential pairs based on layer. In CES, we have access to Hyperlink Stackup Editor. From the ZO Planning tab, we can find the proper trace width, and the tool will calculate the gap. This can be switched if needed. Now that we know the trace width and gap, we can assign these values in our CES spreadsheet. Like Excel, we can copy, paste, and drag copy values to make replication simple. Notice CES provides single-ended and differential impedance values, which auto-update when trace typical and spacing gap cells change. Reusing clearance rules is what simplifies rule creation. For our GPIO nets, we'll set up a special set of spacing rules for both the mainboard area and an area rule for the BGAs. After creating, we can adjust spacing rules by layer using a simple spreadsheet. Note, net classes and clearance classes are shared between all area rule definitions. For nets that require electrical-based rules, we will use the constraint class section. A constraint class provides the following: length, via count, length matching, topology definition, virtual pin assignments, etc. In this case, we are missing a definition for our HDMI nets. In addition, the HDMI constraint class will separate out the differential nets in a subclass called diff. Designs with differential nets require special attention, as you need to tell the tool what two nets belong together. With CES, we can do this automatically with built-in automation. For this design, all the diff pairs nets end with _P and _N. Once all have been added to the list, you simply click apply and you're done. We have a constraint class called RxTX_SO, which is all differential pairs. We have a requirement that all nets for Rx or Tx be matched within a certain length, but we don't care about the overall length. We could use length minimum and maximum, however this would require us to route a few nets first. Instead, we'll use a matching rule, which is far simpler to manage. From a length matching column, we can set the same name for all the Rx and Tx nets and then set a value. There are certain conditions where controlling net topology is required to ensure proper timing and signal integrity. Some examples might be multiple onboard DDR devices, clock distribution networks, etc. In our case, we want our I2C bus to maintain proper topology, as the traces will be long and run between multiple devices. Using a custom topology, we can define the from-to connections for the entire net. There's more than one I2C net, so to simplify management, we'll save the topology information to a template. Everything we define in a constraint class can be saved to a template. The benefit is we now have one place to manage a rule for 2 to hundreds of nets. For a topology template, we'll be asked to verify from-to connections are correct before applying. To show simplification, I've set a max internal layer trace length. Notice when changed in the template, it automatically changes for all nets assigned to this template. Clearance rule reuse is the real power with layout. Kind of like templates, we can set up a few different sets of clearance rules and then assign them between different net classes. This is unlike most layout tools, which require each net or class of nets to have their own clearance definition, making management far more difficult. One of the simplest forms of routing automation is fanning out pins from SMD devices, which is the process of using auto-routing technology to route short traces to a via so a net has access to internal layers. To take full advantage of automated fan-out, some rules will be required. Additionally, defining what direction traces will be routed is highly recommended. For our design, we have several BGAs and some large pin count connectors. The BGAs are simple: set the direction for fan-out and go. For non-BGA parts, you have more choices. In the case of this connector, I would like most of the power and ground pins routed to the outside and all the diff pair pins to the inside to minimize length discrepancies. To achieve this, we'll set the fan-out direction for outside, select the power ground pins, perform fan-out. Next, adjust the fan-out direction to inside, select the component, and fan out the remainder. For tight designs or BGAs with fine pitch ball spacing, placing vias in the SMD pins or passives or even BGA pins is required. Being able to adjust settings on the fly and having finite control makes the process much easier. In our case, we need to place decoupling caps directly under the BGA, which requires vias to be placed in the pins. Let's take a quick look at one of the many helpful features. Notice as I zoom in on this phi chip, how net lines disappear and reappear when I pan to the right. This setting is called dynamic net filtering, which makes it much easier to see what you're routing without having to change settings. Routing our design would most likely take the most amount of time. However, using some of the things we've already covered, along with interactive auto routing, this may not be the case. Using sketch routing, we can quickly route sections of the design and even experiment with different part placements or design rule options. Another helpful netline filtering option is marking nets. Using Layout Net Explorer, all the net and constraint classes from CES can be seen along with any of those you create. Let's mark the RxTX SO class as we'll be routing these next. Again, using sketch routing, we can select all the nets from the back section of this connector and route from the EPIP device to the connector. All these nets are differential pairs and following rules we defined earlier in CES. Lastly, we will route the short traces from the termination resistors to the connector. We performed all this routing in less than a minute. Next, we're going to run a quick experiment. We'll route the other half of the RxTXSO net group using interactive hand routing and then sketch routing and see which is faster. For time reasons, these have been sped up, but it was all done in real time for both tests. If you're not using interactive routing or advanced rules to define your differential pairs, I'm sure you could imagine how long these nets would take to route a single trace at a time. Next, we'll route the same nets again, but this time using sketch routing. Now you can see why using routing automation can reduce your design time by 50 to 90%. In this simple experiment, we saw roughly a 5x time difference in routing. Our next design task after routing is to length match nets if required. If you remember, we set length matching rules on these RxTX nets earlier. The back half of the connector and the front half all need to be matched within 200 thousandths. First, we'll work on a few nets using manual interactive tuning. To start manual tuning, we select a segment where the serpentining will start. Right-click, choose Tune Routes, choose Manual Tune. A box appears with the start of a serpentine inside. Using the drag handles, we can horizontally or vertically add more trace. Also notice the tuning meter on our cursor. This is giving us real-time feedback on where we are for length. The tune sections can also be moved around as it's considered a special object. If a tune section is no longer needed, it can be flattened and serpentining removed. Multi-trace auto-tuning is also available as an option to reduce tuning time even further. You may want to consider this option if 15% or more of your design's nets require length matching. Within a few seconds, we tuned all 12 differential pair. To ensure all traces were matched, we can open the target length dialog. From here, we can see the current length for all nets that are part of our length matching group. Additionally, we can see the deviation from the max or minimum rule. For matched groups, we can select a target length to which all others will match themselves to. Like the manual tune function, all the serpentine areas are objects, so they can be selected and adjusted or moved if needed. Teardrops are not always needed, but when we have to use them, it should not be a cumbersome task. Being able to control the length and width is mandatory, otherwise some designs may require adjusting far too many traces to make sure a teardrop can be added. Let's jump over to an area not routed to see how we can selectively control what vias or through pins will get teardrops. Again, using sketch routing, we will quickly add traces to the phi circuit. The global setup for teardrops has been set so only the selected layer or objects will receive teardrops. There may be times when we want to make quick adjustments to an electrical constraint. To our surprise, it looks like we forgot to define our phi diff pairs. For only a few pairs like this, we'll use the constraints panel inside layout. We've now been notified by our engineering lead of a change to the 100 ohm trace and basic requirement. We could rip up the traces and reroute, but to fix, we'll just change the trace width and then let the tool do the rest by using repair selected. We've already covered conventional teardrops, but there are occasions when curved are required in tight spots, or to fix fabrication issues so the manufacturer does not have to modify our designs. Like conventional teardrops, curved can be customized for each situation and applied to only those items selected. Notice how the copper being added is not uniform between each side, but fills in as needed to make a conformal curve. Typically, one of the last major tasks to complete in a board design, aside from documentation, is creating plane area. Many of today's designs include 10, 20, 30 plus plane areas or very complex board outlines, all of which can consume a good portion of the design time. One type of circuit design that requires special attention is power supplies. We need to keep inductance down and create copper areas that can handle high current. Doing this with traces is not the best option. Using planes and solid connections to pins is the simplest method. Drawing simple rectangles and circles using merge and cut commands, full shape corner manipulation, and setting per shape plane thermals allows us to create complex plane areas in seconds to minutes, not minutes to hours. Additionally, when dealing with through-hole pins in power sections, it's far less time-consuming to modify pin thermal settings based on layer usage rather than at the library level, giving us ultimate flexibility. Earlier, I mentioned complex board outlines. We can now create full board area planes in seconds by taking advantage of this shape and not having to replicate it. Having one central location to control what nets are assigned to a layer, which net is allowed to use the route border as its plane shape, and setting the state of the shape facilitates proper design management. Working with a 4 or 40 layer board, at some point we need to create embedded planes. As I showed earlier, using simple rectangles and circles instead of drawing complex polygons dramatically reduces the time it takes to create embedded planes. Let's go through two examples. First, we will create an embedded plane using rectangles and merging of shapes. What's the advantage of taking the time to merge shapes? It allows us to easily move the shape at any point and change properties. Next, we'll create the same shape using rectangles and merging subtracting of shapes. Having this option gives us flexibility as each design poses different challenges. To finish off this plane area, we'll round all the corners. Layout provides options like this that makes performing shape manipulation less painful than most tools. Without using a timer, it looks like the second option is faster for this type of plane shape. If you've been designing PCBs for some time, at some point you've had to fill a plane area with vias or place guard vias around a trace. When placing one by one, this takes forever. We have a requirement with our design to create a ground plane directly under our RJ45 connector and fill with vias. Using stitch shape, we can play with several scenarios and choose the most appropriate, as it only takes a few seconds to process. In case we create more plane areas requiring via fill, we'll save this configuration. Later, when creating a shape, we can then assign this configuration. Now that we've saved a configuration, if we undo our via stitching, we can assign our new stitching configuration. To perform the stitching process, we simply select and right-click over the shape and choose Generate Stitching Vias. In a few seconds, our job is done. Let's recap what we've talked about. Several new technologies exist that can dramatically impact the time required to design a PCB. The core part of PCB design, component placement, routing, and plate creation, can all be made simpler and take less time using the advanced automation technology we covered.